welcome to the Deep Dive. Today we're plunging into something that genuinely blew my mind when I first read about large language models. We all know how incredible these models are at, thinking through complex problems, right? They can reason step by step, tackle planning.
Absolutely. They're powerful tools for that.
But here's the truly surprising twist, and it's a question I want you to maybe mull over as we go. What if this very thinking, this analytical muscle, could sometimes, well, hinder their ability to do something really basic, like just following instructions? So today we're taking a deep dive into a groundbreaking new paper that uncovers precisely this counterintuitive thing. It reveals how explicit reasoning, specifically what's known as chain of thought or COAST prompting, can actually degrade an LLM's accuracy when it comes to instruction following.
Yeah, it's quite the finding.
Our mission today is to really unpack why this happens. We'll look at specific examples. Some are quite odd of when thinking helps versus when it strangely hurts. We'll explore the surprising mechanism underneath it all, and most importantly, discover the clever strategies researchers are developing to fix these unexpected failures. Get ready for some genuine aha moments that will definitely reshape how you think about LLM intelligence. Okay, let's start with chain of thought prompting. As many of you using LLMs probably know, it's that technique where you prompt an LLM to reason step by step before it gives you the final answer.
Right. Show your work, essentially.
Exactly. And it's been an absolute game changer, hasn't it? It's revolutionized complex tasks, math problems, planning, multi-hop Q&A.
No doubt. Huge impact.
Yeah.
And it's not just academic either. Models like DeepSeek R1, Claude, OpenAI's O-Series, they all incorporate COAST-style reasoning.
So it's pretty mainstream now for complex stuff.
It absolutely is. So what's fascinating here is how researchers stumbled upon this surprising downside. Despite COAST's clear benefits in those reasoning tasks, they decided to check its impact on something maybe more fundamental, just, precise instruction following. To do this, they put 15 different large language models to the test. And it was a really diverse group.
15? Wow.
Yeah, ranging from general-purpose models like Llama and Mixtral, all the way up to highly reasoning-tuned models like Claude 3.7 and DeepSeek R1. They evaluated them on two distinct instruction-following benchmarks. First, IFEVL, which uses prompts with simpler, rule-verifiable constraints.
Like write 400 words or mention AI 3 times.
Yeah,
Simple rules.
Exactly. And then Complex Bench, which, as the name suggests, has instructions with more complex compositional constraints, often combining multiple dependent rules.
Okay, so they put these models to the test with their shiny thinking caps on using COAST.
Yeah.
And what did they find when they applied it to these instruction-following tasks?
Consistently and often quite substantially, a performance drop.
A drop.
Yeah, it really stumped them at first because it's so counterintuitive.
It's utterly perplexing.
Yeah.
You gave an example earlier, Llama 3.8b Instruct on IFEVL. Its accuracy dropped from, 75% down to nearly 59%.
That's right, over 16 percentage points lower, just by adding the reasoning step.
Think about that. You add a thinking step, which you'd expect makes it more precise, more careful, and it actually makes it less accurate at following basic rules. It feels like we're missing something fundamental here.
It certainly raised questions.
That's a real head-scratcher,
Yeah.
right? So how did the researchers begin to unravel why this was happening? They didn't just stop there, I assume.
No, definitely not. They conducted detailed analyses, including large-scale manual case studies, to really pinpoint the specific scenarios where reasoning helped and where it, surprisingly, hurt.
Okay, let's break that down. Where did it actually help? It wasn't all bad, right?
Not at all. There were two main areas where COAST was beneficial. First, it significantly improved compliance with formatting and structural adherence.
Ah, okay. Like making valid JSON.
Exactly. Or wrapping output in double quotes, strictly following markdown syntax, things like that. The reasoning seemed to help enforce those rigid structures.
So it acts almost like a meticulous checklist for those kinds of mechanical rules.
Precisely. Take one example. The instruction was to repeat the prompt and put the name in double angular brackets, like name.
Okay.
With COAST, the model correctly repeated the prompt and did the formatting. It passed all constraints. Without COAST, sometimes it just skipped repeating the prompt. The thinking process helped it tick off all the boxes.
Got it. And the second area, it helped.
The second area was with lexical and keyword precision. These are those really specific word or character requirements.
Like use a rare letter 3 times. Or don't end with a period, those fiddly ones.
Exactly those. Very precise constraints. Consider one. Write a cover letter ending exactly with, call me at 631-481-4867 Mart, no period at the end.
Right, which models usually add automatically.
They do. But the code-enabled model correctly omitted the final period to satisfy that exact constraint. It overrode its default tendency. The reasoning likely made it explicitly flag and prioritize that strict rule.
Okay, so for very specific formatting and exact phrasing, thinking helps.
Mm.
But then, the flip side. This is where it gets really counterintuitive, where reasoning hurts.
Yes. One major issue they identified was over-focusing on high-level content and neglecting simple constraints.
Like it gets lost in the weeds of planning the content.
Kind of. It's like the model gets so preoccupied with the big picture planning the substance of the response that it loses sight of simpler mechanical rules.
Like word counts.
Yeah.
Or repeating the prompt exactly.
Exactly. Exceeding word counts, failing to repeat prompts, using capital letters when told not to, appending extra stuff.
Do you have an example of that?
Sure. Imagine instructing an LLM to create a print ad, a crucial rule. Do not use any commas in your response. And also just repeat the entire instruction first.
Okay, no commas, repeat the instruction. Simple enough.
Seems like it. But the code-enabled model, while planning out a great ad in its reasoning steps, actually inserted a comma when it repeated the meta instruction part. It broke that simple no commas rule.
Wow. So the reasoning, the planning for the ad, somehow distracted it from the simple comma rule.
It appears so. It's like a brilliant artist so focused on the masterpiece they accidentally knock over the paint can. The complex focus overshadows the simple constraint.
That's a perfect analogy.
Yeah.
And there was another way it hurt, too.
Yes. The second way was by introducing unnecessary content that violates constraints. The model's internal thinking process, while maybe trying to be helpful, can add things.
Like notes to itself. Or explanations.
Exactly. Explanations, translations, little bits of commentary, stuff that isn't part of the requested output, but because it's in the output stream, it accidentally breaks a rule. Take the Italian haiku example. The instruction was, write an Italian haiku, but importantly, no commas in the entire output. That includes any thinking steps shown.
Okay, so the rule applied to everything, not just the final poem.
Correct. The code-enabled model produced a perfect haiku. Beautifully done, no commas in the haiku itself, but its thinking section, where it planned the haiku structure and maybe translated words, that part did contain commas.
Ah, so even though the haiku was fine, the whole response failed the constraint because of the thinking part.
Precisely. The no commas rule applied to the full generated text, including the reasoning. So, a failure.
This really raises a big question then. How does reasoning, this thing we think makes models smarter, actually lead to these kinds of failures? What's happening underneath?
That's exactly what the researchers wanted to understand next. They used an attention-based analysis. It's a way to sort of peek inside and see what the model is focusing on internally. They came up with a metric called constraint attention to track how much focus the model puts on the instruction words, the constraint tokens, during generation.
Like tracking its eyes, metaphorically speaking, to see if it's still looking at the rulebook.
Kind of, yeah. Monitoring its internal focus level on the rules as it writes.
And what does that show? What happened to attention when code was used?
The visual data was quite revealing. When co-prompting was used, that constraint attention trace often flattens out during the response generation phase.
Flattens, meaning it stops paying as much attention to the constraints.
That's what it suggests. It's almost like the model is so busy thinking through the steps, planning its response, that its focus on the specific rules momentarily dips.
Tunnel vision, maybe. Focused on the reasoning steps, forgets the rules on the periphery.
That's a good way to think about it. And they quantified this. The attention drop, the difference in constraint attention between the base model and the COAT model, was significantly larger in the cases where reasoning hurt performance, the Lucy cases they called them.
Okay, so there's a measurable drop in attention to rules when COT causes errors.
Yes, especially in the early to middle layers of the network, which are crucial for formulating the response structure. It strongly suggests reasoning can divert focus from instruction details.
And you mentioned something interesting earlier. The length of the reasoning didn't really matter. Longer thinking didn't mean better following.
Correct. That was another surprising finding. There wasn't a meaningful correlation between how long the reasoning chain was and how well the instruction was followed. So it's not just about more thinking.
It's about the focus of that thinking, perhaps.
Seems like.
Okay, so we have a problem. Thinking can hurt instruction, following by diverting attention. The good news, I hope, is that the researchers didn't just stop there. They looked for solutions.
They did. They actively proposed and tested solutions. They explored 4 different strategies to try and mitigate these reasoning-induced failures, and some were quite promising.
All right, let's hear them. What was strategy number 1?
The first method was pretty standard. In-context learning or few-shot learning. Provide the model with examples.
Show it how to do it right, even with co.
Exactly. They gave it examples, often based on common failure types they'd seen, manually corrected to satisfy all the rules while still showing the reasoning.
And how did that work? Showing good examples feels like it should help.
It yielded only modest improvements here. Better than nothing, but not a huge leap.
Why, only modest?
Partly practical limits, like token length, restricting how many examples you can fit in the prompt, and maybe some bias from the specific examples used. It suggested the problem wasn't just a lack of examples, it was something deeper. Not quite a silver bullet.
Okay, not the magic fix. What was next?
Next, they tried self-reflection. This is a two-step process. First, the model generates its response, including the reasoning. Then
it checks its own work.
basically, yes, it critically evaluates its own output against the original instructions and revises it if it finds errors.
Interesting. Get the model to self-correct. How did that perform?
That showed strong improvements, actually, particularly on the simpler tasks, like in IFEVL. It improved 11 out of the 14 models tested there and was the best strategy for 7 of them.
That sounds pretty good.
Yeah.
Any downsides?
Well, it was less effective on the more complex tasks in Complex Bench. And sometimes, for weaker models, asking them to critique themselves could actually make things worse. Maybe the critique wasn't accurate.
Okay. And I guess it takes longer. 2 passes.
Exactly. It roughly doubles the computational cost because you run the model, then you run it again for the critique and potential revision. So, a significant trade-off.
Right. Cost versus accuracy. Okay, strategy 3.
Strategy 3 was self-selective reasoning. The idea here is to empower the model to decide for itself whether it even needs to use explicit reasoning for a given instruction.
So the model looks at the instruction and thinks, do I need to do step-by-step thinking for this, or can I just answer directly?
Precisely. Let the model choose its approach.
That sounds smart. How did it do?
It achieved moderate gains on the simpler IFEVL tasks and actually stronger results on Complex Bench. It improved all models on that harder dataset.
Okay, better on complex tasks. But was there a catch?
There was a bit of a catch. The model tended to over-select reasoning. It applied CUMI even when it wasn't really beneficial.
So it was good at knowing when reasoning might be useful, but used it too often. High recall, low precision.
Exactly that. It erred on the side of reasoning even when direct answering might have been better or safer for instruction following.
Gotcha. Which brings us to the 4th strategy.
Yes, and this one turned out to be arguably the most effective overall. Classifier selective reasoning.
Okay, what's different here?
Instead of the LLM itself deciding, an external, separate binary classifier is trained. Its only job is to predict whether using commit reasoning is likely to improve instruction following for a specific prompt, compared to just answering directly.
So like an external judge or umpire, it looks at the prompt and tells the LLM, okay, use COMIT for this one, or nope, just answer directly.
Exactly. The classifier makes the call, and the LLM follows that decision.
That feels like it directly targets the problem of when to use reasoning. How effective was it?
Highly effective. It improved performance for almost all models on both benchmarks, IEVL and Complex Bench. And it was the top-performing strategy for about half of the models tested.
Wow. So that external check really helps. What's the trade-off?
The main trade-off is the overhead. You need to train the separate classifier, and it's typically model-specific, so it adds a step and requires training data. But the performance gains were often significant enough to justify it.
Okay, so based on all that, what's the recommendation? How should we approach this?
Well, the researchers suggest a kind of pipeline approach. First, maybe try to estimate how complex the instruction is. For simpler tasks, self-reflection could be good if the cost is acceptable, or classifier selective reasoning is a strong choice. For more complex tasks, where CATAC might be more needed but also riskier, self-selective reasoning should promise, but again, classifier selective reasoning often came out on top.
So it sounds like that classifier selective method, despite the training cost, consistently delivers the best results.
Overall, yes. It seems to offer the most reliable way to get the benefits of reasoning when needed, while avoiding the pitfalls when it's likely to hurt instruction following.
Okay, so stepping back then, what does this all mean for how we build and use these large language models? This whole deep dive into when thinking fails. It really challenges that simple idea that more reasoning is always better, doesn't it?
It absolutely does.
It highlights this critical, kind of overlooked vulnerability, how LLMs process instructions. that sometimes their attempts to think
Sure.
can make them stumble over the basic details.
Yeah, and this research isn't just pointing out a problem, which is important, but it's also giving us concrete, actionable solutions. It paints a much more nuanced picture. Explicit reasoning can pull the model's attention away from crucial details, yes, but these selective reasoning strategies show we can effectively recover that lost performance.
So the path forward isn't necessarily just more reasoning.
Exactly. It's about smarter, more selective reasoning. It's about developing models or systems around models that know when to engage that deep thought process, and critically, when to just follow the instructions directly and precisely.
Which brings us to our final thought for you, the listener. As you reflect on this, here's something to mull over. How might this phenomenon of overthinking in large language models, where they get lost in complexity and miss simple rules, how might that parallel our own human tendencies? Do we sometimes get so lost in complex thought that we miss the obvious simple instructions right in front of us?